Hey everyone, today we are covering section 3.9 of our book, which is called Differentials. And so, really, what today is all about is approximating, and we will be going back to our good friend, the tangent line. So, uh, we have a little warm up. But the warm up is something that you can already do with the knowledge that you have. I encourage you to pause it and do it and then check your work. So here we go. Find the equation of the tangent line to the curve f of x equals x squared when x equals 1. So first of all, we need to know what the point is. So we need to find f of 1, and that's just going to be 1 squared, which is 1. So our point is the ordered pair 1, 1. Now we're also going to need the slope of the tangent line, which we know is the derivative. So I'm going to find the derivative of x squared, and it is 2x. And then, of course, we specifically need to know what this is equal to when x is 1. So we're going to plug in a 1, and we get 2. And so this is our slope. And so then the final step is to write the equation. So we're going to have y minus 1 equals m, which is 2, times the quantity x minus 1. And you can leave it like that, or you could multiply it out and add the 1. So this next piece is kind of trying to generalize this idea. So what is the equation of the tangent line at the point C, f of c? And this is for any given function f. So we have the point, right? We have the c, f of c point. What we're missing is the slope. And taking what we did up here, we just took the derivative and we plugged in the x value. So here the slope will be represented by the derivative evaluated at the x value c. And so now we have the slope and our point, which allows us to write our equation for our tangent line. So this one is going to be y minus the y value, which is f of c, which equals the slope times the quantity x minus our x value, which is c. So this is a general form of the equation of the tangent line. And so you'll see in the box you have a kind of a formula. So the equation for the tangent line at the point C, f of c is given by y equals blah, blah, blah. And so all we've done here is we have isolated the y. So these two equations are equivalent. And instead of memorizing this one, I would just continue to think about it in the way you're already familiar with. But this is just the general form. So you can memorize this or keep thinking about the tangent line the way we've been doing it. And what this is called is the tangent line approximation, also known as the linear approximation of f at c. And so what do we mean when we say that? Well, this idea of local linearity is important. So if you have a function that is differentiable at a given point A, then if you get close to A, so if you get really, really close to A, the graph of f will resemble the tangent line. So this image is trying to show you that. So here we have zoomed into the box, the pink box, and we can see we have the tangent line to this point, which is the point 1, 1. So this is actually the problem that we were dealing with in the warm-up. And you can see that if you have x values that are really close, like basically this whole, I don't know, from like here to here, you can see that they're pretty close. But if you're really close, like this region, the graph almost becomes linear in that area. So the more you zoom in, your function will resemble a line, and therefore the tangent line gives a really good approximation for your function values. And this just can make it easier than finding the point at the exact point on the function. So and now that we have calculators, this is like a little less important, I would say. But the idea is that we can use the tangent line to approximate our function at a point. So let's just write that. It's said a lot. It said like here, and we're writing it. So the tangent line can be used to approximate your function at a point. Ideally, a point close to the point of tangency. So here in this image, the point of tangency was 1, and so you want to stay close. Like you don't want to be approximating like f of 9 using the tangent line. You want to stay close to the point of tangency. Okay, so below we have two images. We have a kind of concave up shape and a concave down shape. And so once again, the idea is that the tangent line can approximate a value of f of x for points close to your a value. So let's say that we have our, let's choose this point. Let's say that this is the a value. And then we draw a tangent line. And so close to, that's not the best tangent line, but we see that in this region, close here, it's a fairly good approximation because the difference between these two is not that big. So if I evaluated my tangent line at B, it would be kind of close to the actual function evaluated at B. Pretty close, right? Not too far off. But the further out you get, the worse the approximation becomes. Now, what I wanted to just show you here is that when you're dealing with concave up, the tangent line is always going to give you a value less than. So notice the tangent line is below the curve, so the tangent line is giving an underestimate. This is when you're dealing with concave up. What about when you're dealing with concave down? Well, you can imagine it's going to be the opposite. So if we have our value A, and again we draw a tangent line, now you can see any value that your tangent line pops out is going to be a bigger value than the actual function. And so here the tangent line gives an overestimate. And so in our book, it doesn't really ask you about this, but you could see this on the AP exam. So it could say to, find me this approximate value and state whether it is an overestimate or an underestimate. And so for that, you really need to know what the concavity of the function is. Okay, so let's try some examples. So let's say we have f of 3 equals 5 and f prime of 3 equals 2. We want to estimate f of 3.1. So in this case, we actually can't find f of 3.1 because we're not given the function f. All we know is that f of 3 is 5 and f prime of 3 is 2. And so this, because it's f prime, this is the slope slope of tangent at x equals 3. And then this is giving us an ordered pair, 3, 5. So you can certainly use, I'm going to scroll back up, you can use this formula that was given up here, right? F, here your C value would be 3. This would be your C, this would be your F of C, and then the 2 would be your F prime of C. Or just write it out in point slope form. Just write the equation of the line in point slope form. That's what I would recommend. So we're going to do, let me switch back to gray. So we're going to do y minus 5 equals, the slope is 2, and then we have x minus 3. And you could leave it like that, or you can distribute and add the 5. I'm going to add the 5, and I'm not going to distribute right now. And so this is the tangent line approximation. So this is our tangent. And so when we go to find f of 3.1, we are going to use the tangent line, and it is an approximation. So f of 3.1 is not equal to, it is approximately equal to the following. You're just going to use the tangent line, and instead of x, you're going to substitute in the 3.1 because that's the x value. So this would be 5 plus 2 times 3.1 minus 3. And then now I'm going to switch to an equal sign because the thing I just wrote is indeed equal to f plus 2 times 0.1. And 2 times 0.1 is 0.2. And 5 plus 0.2 is 5.2. So we have found our approximation. So f of 3.1, oopsies, f of 3.1 is approximately 5.2. To know if that was an overestimate or an underestimate, we would need to know the concavity of the function, and in this one, that wasn't given, so this is all we could say. Okay, so what about this next one? So in this next one, we're actually given the function h of x. We are going to write an equation of the line tangent to the graph of h at x equals 1/2, and then we will estimate 0.49. And then I want us to find the actual value on the calculator and compare the two. So in this one, we can find the actual value because we are given the actual function. In the previous example, we were not given the function f, so we could not find the actual value. So let's try it out. We need to know a few things. We need to know what the point is. So we need to find, so at 1/2, we need to know the y value. So we need to find h of 1/2. And that's going to be 8 times 1/2 cubed, and 1/2 cubed is 1/8. 1/8 times 8 is 1. So our point is 1/2, 1. And now I want to find the derivative evaluated at 1/2. So h prime of 1/2. So we're going to do this all in one step. So we're going to find the derivative, bring the 3 out front. We get 24 and then x squared. And in this case, our x is going to be 1/2. So we're doing 2 and 1. Find the derivative and substitute in the 1/2. 1/2 squared is 1/4, and 1/4 of 24 is 6. And that is our slope. And so we can pretty easily write the equation of the tangent line. So we're going to have y minus 1 equals 6 times x minus 1/2. Again, up to you. If you want to multiply it out, leave it like this. At some point, you're going to have to do some arithmetic, but I'm going to add the 1. I'm writing the 1 in front, really just to stay consistent in case you guys choose to use this formula in the box up here, this one, because they write the f of c here, but you can certainly write it at the end since it's just addition. Okay, so we have our tangent line, and so this is the tangent line. And if we want to estimate h of 0.49, we would just do 1 plus 6 times 0.49 minus 1/2. And then let's see. So 0.49 minus 1/2, remember 1/2 is 0.5, so 0.49 minus 0.5 is negative 0.01. And so this is going to be 1 minus 0.06, which is 0.94. So that is the estimate. Then we can use a calculator to find the actual. So the estimate is 0.94, and then the actual would be 0.4, oh geez, 8 times 0.49 cubed. Okay, I didn't do this one ahead of time, so I'm gonna try to do it on my phone real quick. So 0.49 cubed times 8. So I'm getting so this is what I'm getting here, 0.941192. Hopefully that's right. I'm getting it on my phone. And you can see how close these are. And again, they are close because 0.49 is very close to 1/2. But had that been like h of 2 or something farther away from the point of tangency, it would not have been such a good approximation. Okay, so that is the idea of this tangent line approximation. And so now we're going to talk about differentials. And differentials are just another way to approximate your change in y. So let's just do some examples and then you'll see. So first we need to talk about this difference between delta y and dy. So dy is called the differential of y, and dx is called the differential of x. And so I think the best way to illustrate this is to draw out an example. So we're actually going to do an example to illustrate what this whole big idea is, and then we'll do some more examples to practice. So first off, we already know what delta y represents. Delta y represents the actual change in y. Using whatever your function is. Using the actual given function, it is the change in y. So let's talk about this. So we're going to practice using the square root function. So I'm going to just sketch the graph of the square root function. So this is going to be the square root of x. Okay, so now I'm going to choose the point. This is not drawn to scale, okay? I'm going to choose the x value 4. And we know what the y value is. When x is 4, square root of 4 gives us 2. And then another number we know would be 9. And the square root of 9 gives us 3. So here, if I asked you for the change in y, well, let's just remember that we have here, we can make a little triangle. and this would be the change in x, delta x, and this would be the change in y, delta y. And so with these numbers, since they are friendly numbers for this function, it is pretty easy to see what's going on. So here, the change in y, or the delta y, is the square root of 9 minus the square root of 4, which in this problem was 3 minus 2, which was 1. So it's pretty easy to see that the change in y is 1, and it should also be easy to see that from the graph. And then the change in x was the two x values subtracted, so 9 minus 4, and in this case that was 5. And so you could find the average rate of change between these 2 points, because the average rate of change is just the change in y over the change in x. But what if we didn't choose such friendly numbers? So we are going to make another sketch. I don't know why that grew so much. Okay, so once again, we have our function f of x equals the square root of x, and we're going to have 4, and the square root of 4 is 2. So I'm still going to choose 4. Now, instead of choosing 9, let's choose something much closer to 4. So I'm going to choose like 4.1. Okay, something very close to 4. I'm going to sketch it kind of further away, just so that things aren't too squished on their graph. So this is not drawn to scale. And so what would this y value be? Well, without a calculator, we don't know the square root of 4.1, but we do know that the y value is going to be, shoot, I ran out of room. Okay, squeeze it in. We know that this y value is going to be the square root of 4.1, which right now we don't know what that is. Okay, so what is going on? Now, if I asked us to find the change in y again, now we would have the change in y is the square root of 4.1 minus the square root of 4. And we know the square root of 4, but we don't know the square root of 4.1 because, whoops, I forgot my calculator today. So this is where the tangent line is going to come in, and this is where I'm going to really explain the difference between delta y and dy. So here, as you recall from the previous example, we had our delta y and we had our delta x. Now, what I want to do is I'm going to draw the tangent line. So let's pick blue. So I'm going to draw the tangent line. The point that we are working with is the 4. So I'm going to choose that as my point of tangency, and I'm going to sketch my tangent line, which will not be drawn very well, but ooh, not too bad actually. And so the tangent line, we know, is you find the tangent line using the derivative. So the slope of the tangent line is dy dx, is the first derivative, dy dx. And so now what's going on here is that this whole thing, this, instead of delta y, this is dy. And you can see that dy is just a little bit off from delta y. It's just a little bit off. It is close. Right, they are almost the same. Dy is an approximation of delta y. So dy approximates delta y. And then this horizontal is still dx. And so we can see that in these problems that we're working with, in these differential problems, dx is the same as delta x. So dy is an approximation, but dx is not. They are the same. So sometimes you'll see in a problem it'll give you dx, and sometimes it will give you delta x. And so this is the visual of what's going on. But let's say now that we actually want to really find what the square root of 4.1 is. Let's say we want to find it. We're like dying to know what it is, and we forgot our calculator. So let's find dy dx, which we can do. Oops, I don't want that color. I want this color. Okay, so we can find dy dx because we know f of x. So I guess I should be calling this y technically, not f of x, but whatever. So it's f prime of x, okay? The derivative of y with respect to x. So the derivative of square root of x, remember that's x to the 1/2. So when you take this derivative, you get 1/2, and then you get x to the negative 1/2, which is really just square root of x in the denominator. So you get 1/2 root x. And so we have this ratio. If you think about dy dx as the ratio of these sides of the triangle that we drew, if we only wanted dy, we're going to multiply both sides by dx. Whoa. So we're going to get this. And this is what is known as the differential of y. So this is like what we're working with today. And so now we can find dy because we know our x value and we know our dx. So when x equals 4, which is what we're working with here, we're working with x equals 4, what is this dx? Well, the goal is to find 4.1, so in this case, the dx is going to be 0.1. If it was 4.2 we were working with, it would become 0.2. If it was 4.3, it'd be 0.3. And so we're just going to substitute those values in. So we're going to have dy equals 1/2 times the square root of 4. That was not the right color. Times dx, which is 0.1. And then we're just going to do this. So 1/2 root 4. Root 4 is 2. We have 1/2 times 2. That's 1/4. I'm going to write it as 0.25. So we have 0.25 times 0.1, and that's 0.025. So this is what we're getting for dy. This is what we're getting for dy. And remember, dy approximates delta y because from this, dy should be quite close to delta y, depending on how far away you go from your x value. So dy, let's write it out now. Dy approximates delta y using the tangent line. Slash the derivative, right? Using the tangent line, or you could think about it as using the derivative. And so here we are getting that this delta y is approximately, so we still haven't found the exact, is approximately 0.025. And the delta x is 4.1 minus 4, which is 0.1. And remember that the delta x is the same as the dx. This is also the dx. And so the idea here is that now that we have found the approximate delta y, you can find the approximate square root of 4.1. Because if you know, so here's another little aside. I'm just trying to really explain this thoroughly so that you guys understand the concept of what's going on. I'm sorry if it's too much for you, you can fast forward. So what we're thinking about here now is that we know that square root of 4.1 minus square root of 4 is approximately 0.025. And so if I want to find the square root of 4.1, I can just say, well, that's going to be approximately 0.025 plus square root 4. And we know square root 4. Square root 4 is 2, and so 2.025 is what I'm getting. And so if you go to a calculator and you type in square root of 4.1, you get 2.02484, blah, blah, blah. So that is quite close. So back in the day, before our good old calculators could calculate square root, this was a way to think about it. Okay, so here's the actual definition of differentials. So if you have your function y equals f of x, and it is differentiable on an open interval containing an x value, then the differential of x, which is dx. So dx is the differential of x, and then the differential of y is dy, is represented like this. And that is what we did right here. Remember, we took the derivative and then we multiplied it by dx. So dy is equal to your derivative evaluated at your point times dx. And remember that dy is an approximation of delta y. And therefore, you can approximate delta y using this concept. Okay, so let's try a few more examples. So we are going to do this first one. Find dy, then find the value of dy given x equals 2 and delta x equals negative 0.1. So dy is going to be equal to the derivative of that function, so 4x cubed minus 9x squared plus 5, that whole thing times dx. That's all there is to it, okay? Now so that's dy. We did step 1. Now we're going to find this given x equals 2 and delta x equals negative 0.1. Remember, this means dx equals negative 0.1 because delta x and dx are the same thing in these problems. So let's go for it. We're going to have 4 times 2 cubed minus 9, 2 squared plus 5 times dx, which is negative 0.1. And then we're going to break this down a little bit more. So 2 cubed is 8. 8 times 4, 32. So I have 32 minus 9 times 4, 36, plus 5 times negative 0.1. And that's negative 4 plus 5 is 1. So this is actually just negative 0.1. That's it. We did it. So this would approximate, so really what this would be doing is it is approximating the change in y when we are working with the values 2. So these would be 2, so it'd be y of 2, and it would be y of, so it would be 2 minus 0.1, so it'd be 1.9. So you could find the actual change. This one's actually not the best approximation, but that's because of the graph. So if you graph it and you see the tangent line, you'll see why it's not as good of an approximation. Okay, one more example. Use differentials to approximate the square root of 9.2. So for this type of a problem, you would first want to always identify what function you're working with. And here it's the square root function. And then two, you're going to want to identify your x value and then your change in x. And so what's the closest square root we know? 9. So we're going to say x is 9. And then I'm going to say delta x is 0.2. Okay. And now what? So there are some different ways you could do this problem. I'm going to show you one way, and then I would encourage you to think of a different way. So let's use differentials since it says to use differentials, but you can also use the tangent line approximation. We're going to use differentials. So dy is going to be equal to the derivative of the square root of x, which we already did earlier. It's 1 over 2 root x dx. So we have our dy. Now, remember that we know the x value and we know the dx because delta x is dx. So dx is 0.2. So we're going to substitute these values in. So we're going to have 1 over 2 root 9 times 0.2. Okay, square root 9 is 3, so it looks like we have 1 over 6 times 0.2. 0.2 is 2/10. And so this is 1 over 30. So I'm getting 1 over 30 as my dy. Okay, so now we weren't asked to find dy. We were asked to approximate square root of 9.2. So this is how I would recommend, or you can think about this in lots of different ways. How I think about it is I think about actual delta y would be square root of 9.2 minus square root of 9. This is what the actual change in y would be, which means you could rewrite this as delta y plus root 9 equals square root 9.2. So we have the square root of 9.2 isolated. So we have this, which is helpful. And now the only thing is we don't know delta y, but we do know dy. And dy is an approximation. So this is approximately equal to dy. And so we're just going to replace that and we're going to say that, so I'm going to put 1 over 30 plus root 9. Now this is not equal to, it is approximately equal to 9.2. And then we know what the square root of 9 is. That's why you want to make sure you pick a number that you actually know the square root of. And then 1 over 30 is 0.033333. And so this is 3. Which is going to be 3.0333 repeating. So square root of 9.2 is approximately 3.0333. And then let's say you go to a calculator and you just find the square root of 9.2, and it is, so from a calculator, you get square root 9.2 is equal to 3.03315. And so as you can see, these are close, very close. So I didn't do an example of like all the types of the homework problems, but using this information, you should be able to figure them out. And we can certainly go over some more examples in class. See you soon.